Hi everyone, we're now looking at areas of triangles. So from law school we know that the area of any triangle is equal to half the base times the perpendicular height, not the sloping height. And we reviewed this briefly looking at right angled triangles in the preliminary exercises. Now here we have a non-right angled triangle. It's triangle ABC. We've marked in D with the perpendicular to help us find the area. And in this case, we're looking at angle C over here. And the sine of C would be H opposite over hypotenuse, with BDC being a right angle. And the sine of C will be the opposite divided by the hypotenuse, which is H over A. So if we rearrange that, we can find out the height H is equal to A multiplied by sine C by rearranging this equation. Now, if we're looking for the area is equal to the base times the perpendicular height. We now know the perpendicular height is A sine C, so half of the base, which in this case happens to be B, times by A sine C, the perpendicular height, which if we simplify it comes to half AB sine C. And we're going to call that equation 1. And what that does is it shows us that we can find the area of any triangle by halving the two lengths on either side of one of the angles, and then multiplying it by sine of that angle. Now, what if we have an obtuse angle of C? Well, we know from lower school that we take this base here, we take this height here, we multiply them together and halve them. We can find out this height here by first finding that angle there, which is 180 take angle C, which is this angle. If we find the sine of that, to find the sine of that, we take the height divided by the hypotenuse, which is A, rearrange it as per the last example, we get A sine 180 take C. Now, from the last video, we know that sine of 180 take C is just sine C. So we can substitute that back into the equation. So instead of being H equals A sine 180 take C, we're just going to rewrite it as H equals A sine C. Substitute that into our normal area formula, half base times height, the height being A sine C, there it is there. Rearranging it, half AB sine C. So it doesn't matter whether we're looking for the obtuse angle or the acute angle. In both cases, the equation for the area of a triangle is half AB sine C. So half of the two lengths on either side of the angle that we're looking at, and then multiply that by sine of the angle. So let's look at an example. Here's a triangle, here's an angle, here are two sides. To find the area of that triangle, we go half times this length times this length, the two side lengths on either side of the angle, multiplied by sine 35, and we get 30.2 centimeters squared. Easy. Here's an obtuse angle, same deal, half that length times sine of 105, there it is there. I don't know if I'll put that into my calculator. There it is there, I think, half, 7.2 times 4.9 sine 105, bang. Remembering to have your calculator in degrees mode. Here's example 3. Now we have to be a little bit more careful with this. We're given the angle, we're given one side, we haven't been given this side, but we do know the area. So if we try and solve that equation, if we construct it here, which I did, the area, 7, is equal to half of 4 times some value we don't know, sine 70. Punch that into our calculator. I think that's it here. And then solve for x. So x is our unknown. It'll give us 3.72 or 3.7 to 1 decimal place. Now, that's good so far, but what if we want the angle itself given an area? Now we have to be a little bit careful with this because there might be an obtuse case like this from this example where the 5 centimeters comes out this way and the 4 centimeters is there, and we have to find the area as per the previous cases. The calculator will give us both values if they exist, and to make that work we have to set a bounds for the sine curve. So to do that, tell it to only give you the angles between 0 and 180, and it will give us these two values here. If you don't put this bound on, as you can see it's here on your calculator, you will get all sorts of weird and wonderful values coming out. So strongly advise, do this. You can read the longer version, that's for all values of x, but it's much easier just to set a bounds, as I've done there. In this case we find out there are two values. X can be 44 degrees, the acute angle, or it could be 135.6. Now if you're dealing with finding the angle given the area, make sure that you check for both cases and don't just put 90 in here, because that would only show you the acute angle. So once you've done that and you're comfortable with the calculator work here, attempt exercise 1B. Thank you everyone.